I'm talking about the Lunar Atmosphere and Dust Environment Explorer, and I won't be going into very much depth on the science today because that's really the province of the PIs and the science team. So I'd kind of like to, not speak to a lot of what they're working on and should be reporting themselves. So you're going to see a fairly superficial talk today, and I apologize for that, but do come to the other talks and the posters. And with that in mind, let's see. It's not in presentation mode, so okay, we're going to do it that way. Just to give you an idea of what's going on, these are all the talks that are being given that address in some way the lunar exosphere and dust environment. And so there's like a dozen of them, many of them, most of them, as a matter of fact, related to LADI. And is there some way I can do the swiping thing on this? Because it's not in the mode of... How do we get the presentation? Great. Super. Thanks very much. And so these are the talks, and these are the posters. I don't want to spend too much more time on that. Just, you know who you are. There's a lot of stuff coming out of LADI right now. Please attend these talks if you want to hear more in-depth science. So the moon is not a quiet place. There's a lot going on all the time. So sitting there in the solar wind a lot of the time, sitting there exposed to the radiation from the sun, the sources of an exosphere and of dust above the surface are many. Photon-stimulated desorption can actually desorb atoms and molecules off the surface. Impact, obviously, going on today. I was just talking to Mark Robinson about how many new craters they see. All the time there's new impacts going on, releasing vapor, and also lofting ejecta into the environment. Thermal desorption takes place, as I'll say in just a few minutes. The thermal environment of the moon is painted out by Diviner very clearly, cycles materials through very, very high temperatures on the day side, very cold temperatures on the night side. Solar wind is being delivered to the lunar surface regularly, with the exception of going into the geomagnetic tail, and we'll talk about that in just a second. And there may also be regolith chemistry going on here, the hydrogen that's coming in from the solar wind and other species coming in from the solar wind interacting with the native atoms in the regolith grains themselves and producing new chemicals. Sorry, this is supposed to be on and live. Are you having a hard time hearing me? Okay. Where was it? Okay, interior outgassing too. Not only is stuff coming from the outside, and not only are we getting processes going on the lunar surface, but there's also gases coming out of the interior of the moon. Once upon a time, there were a lot of gases coming out of the interior of the moon when volcanic activity was ongoing at the lunar surface. But now, today, we see products of radioactive decay. Potassium 40 is giving Argon 40. We see that coming out of the interior. And helium should also be coming out as alpha particles are decaying in radioactive materials. Finally, the same solar wind that's coming in and donating species to the surface is also creating sputtering. So what you see coming out of the moon, off the surface, is a reflection not only of what's coming in from the outside, but also what the moon is made of at its very surface layer. Transport. Ballistic hops is the way you get around on the moon because it's a surface boundary exosphere. The atoms and molecules in the exosphere do not collide with one another. They're hopping from place to place. There's photoion pickup. Sometimes that produces loss, which is down here. When a photoion is created in the solar wind, it gets accelerated in the direction of the electric field of the solar wind. Half the time, that takes it right back into the surface again. Half the time, it takes it away, and it's lost forever. But you can recycle materials this way using the photoion pickup approach. Of course, dust transport may also be a source of exospheric particles because the dust particles themselves are sputtering and desorbing and so forth. So there's a lot of things going on in the source and transport area. In terms of losses, photoionization, as I mentioned earlier, is one important way. Genes escape because the day side is so hot. Certain species like helium are being lost even as they're being delivered by the solar wind. And then, of course, there's cold trapping. There's temporary cold trapping on the night side, and then also permanent cold trapping at the poles where the sun never shines. The moon's not alone in this kind of surface boundary exosphere class. Mercury has one. All these other objects in the solar system would have surface boundary exospheres as well. So it's the most common form of atmosphere in the solar system. And so for that reason, it's important to understand them. What are the sources? What are the sinks? What are the processes by which such an exosphere evolves? And by going to the moon, Earth's nearest neighbor, we can answer the questions related to this nice terrestrial body, a silicate body like this, and maybe learn something even about the outer planets' moons by understanding what things are being delivered to it, which is also taking place out in the outer solar system, and what things are being natively derived from those bodies. And also mention that dust dynamics that occurs at the moon is also going to happen at these other places too, and I think we've already seen that in the outer planets. So dust is present on the lunar surface, obviously. The astronauts got dirty. But there's evidence from the very beginning of our exploration of the moon back in the 60s that dust is being somehow elevated above the surface. And the surveyor images indicate that after sunset, the sunlight was actually being forward scattered through some layer of dust just a few meters off the surface at the local horizon of the surveyor, in this case Surveyor 7. And so, okay, that's kind of interesting. LADEE wouldn't be able to address that until it actually smacked into the surface, and by then it would be dead and wouldn't be able to answer that question. But it can address this question down here. The Gene Cernan and Apollo orbital imagery saw evidence of excess illumination that couldn't be explained by something from the sun, either the corona or the zodiacal light in the inner solar system. So that's one of the mysteries that LADEE was meant to address. And this is our payload. Many of you have seen this before. We have a neutral mass spectrometer that sniffs the gases basically around the moon. So as LADEE flies around the moon, it's basically inhaling those gases as it goes. The ultraviolet and visible spectrometer, UVS, measures emissions from exospheric species. So it's a standoff instrument. It's a remote instrument looking, for instance, two key elements that it was looking for were potassium and sodium in the exosphere, well known from ground-based observations, but never systematically mapped. So this is a terrific opportunity to do the systematics. Also, the lunar dust experiment, which is an in situ dust experiment to measure locally at the altitudes of LADEE what the particle flux is, what the particle density is that's been lofted off the surface of the moon. This is LADEE's orbit after we got into orbit around the moon. I didn't want to go into detail about how we got there, but basically the science orbit took us very close to the lunar surface on the sunrise side, and in fact the orbit was maintained in such a way to preserve the periapsis altitudes at the sunrise terminator. We went higher in a more eccentric orbit over the sunset terminator. That was in order to keep the orbit a little more stable. We didn't have to use quite as much fuel in order to maintain that. We needed to maintain this orbit for a minimum of 100 days of science operations, and this shows you the coverage. The top color here is 1,000 minutes in a 5 kilometer by 5 degree bin, so this gives you an idea of the coverage. And it's a log scale going down into blue. And this is where we impacted the moon at the end of the science mission. Thanks to Pierre Williams at UCLA, I've got this data set that they produced from diviner bolometric temperatures. This is sort of a diurnal curve, but it's actually an instant in time, if you will. This happens to be at a time when the local meridian, the central meridian of the moon was a little past noon. This is the temperature ranging from about 100 kelvins to almost 400 kelvins. Why am I showing you this? Because the surface temperature is tremendously important to atmospheric species. Gases that can condense at 100 K, which you find on the night side of the moon, will condense there. And there happens to be one well-known one that we know of. Gases that do not condense, that have mean residence time on surface grains, even at 100 Kelvin, that are short, will follow this funny NT to the 5 halves, where N is density, T is temperature to the 5 halves. So that means when the temperature goes down, the density that you are measuring at the surface and above the surface goes up. So it's kind of a funny inverse relationship. So this is actually what's going on with exospheric particles at the moon. You can imagine one starting off here near the terminator that gets launched by phonons in the regolith grains, and it leaps up into the sky and then drops back down in its ballistic orbit. Once it encounters the night side where the temperature is no longer high, it is receiving less energy from the vibrations of the regolith grains and hops around for shorter ballistic lengths. And it may stochastically end up back on the day side again, where it begins hopping over larger scales. This is a little thing put together by Mehdi Benna, who you will hear from later on in this conference. And I thought it was a nice illustration of what is taking place atom by atom on the lunar surface. And I have a little set of animations here to kind of give you a sense of what that really means for different species. I'm going to show you two noble gas species. The first is, it should be Argon. And this is at the night side temperatures. And now we're increasing the temperatures. And you can see what happens is they started off here basically clustered at the bottom. And now they've gotten past their non-condensable phase, and now they're jumping up into the sky. And in fact, as you continue to increase the surface temperature down here, they will get more and more agitated, more and more energetic, and the scale height of that exosphere will change systematically over the day side. So that's all that is attempting to show. Yes, I know it's a canister and they can't get out of it. That's not like the moon, but it does illustrate the condensable nature of Argon 40. If you're at lunar night side temperatures, most of those argon atoms are resting on the surface. Their mean residence time is very, very, very long. So the next one illustrates what happens with neon. We didn't look for neon going into the mission, but it turns out neon is there. It's being delivered by the solar wind to the lunar environment all the time. And neon doesn't condense at those night side temperatures. And so when you heat things up, all they do is they just get more agitated and more energetic, and their scale height changes. And so this explains a lot of what we see in the noble gases at the moon, and Mehdi Benna will talk about that more later on. So thanks for the animations. Let's go back to the slides. Oh, here we go. Thanks. This is a well-worn graphic from Hodges and Hoffman. This is Argon 40 as seen by the LACE experiment, the lunar atmosphere. Oh, that's interesting. It's a feature. I'm assuming I didn't do that. Okay, sorry about that. LACE was not able to make measurements on the day side. LADI did. And we painted out the rest of the picture for Argon 40. Mehdi Benna, again, will talk about this in great detail. But a whole half of the diurnal cycle on the moon, as far as Argon 40, its leakage out of the interior, its transport across the day side into the night side, the condensation on the night side, that picture is now much, much more complete. And there are differences between what we see and what was modeled as a result of not being able to make those day side measurements. So I'm not going to go into great detail on that. I am going to mention, however, that we did see, like I said earlier, we did see neon 20. And this is the night side density profile. It follows essentially that NT to the 5 halves equals a constant kind of exospheric distribution. We also saw helium, and the difference between these two things, apart from the fact that there's a factor of 5 in the mass, is mostly about the ballistic trajectories, the ballistic lengths over which these things jump. So helium, at the same temperature as neon, is going to have a higher velocity. Its ballistic velocity will be higher, and that means that it can reach farther on any one hop. And so that tends to kind of smear out this morning sunrise peak. The density drops here for neon just as a result of the fact that the real estate that was once at 100 Kelvin is now crossing the terminator, going into the day side, warming up, and releasing the neon, which then at LADI altitudes is a much lower density. That's actually surface density. So with NMS, we've managed to identify a number of species. This is our required species list. We were supposed to either measure these or push down their upper limits, and so we've done that with methane. We haven't seen it. Oxygen, let's see, we have a detection of OH, we believe, that I think Mehdi will talk about. Possible detection of H2O. It looks as though we see carbon monoxide in the form of ions on NMS, and it looks like we might see SO or SO2 at a limit I'm sorry, we did not see it. So the upper limit is actually below what we were required to go for. Aluminum looks like it's shown up in the mass spectrometer, and it looks like we've seen calcium ions from the mass spectrometer as well. So we're filling out that list, and further analysis of the data is going to get us even further down and maybe reveal some surprises. Okay. Getting into the UVS data now, I just want to show you, this is a picture of sodium abundance as measured by the ultraviolet spectrometer over the course of part of the mission, 2 lunations. And what I'm trying to show you here is the sodium variations that systematically go up and down from lunation to lunation. While in the magnetotail, the sodium actually decreases. And what's going on there is that the solar wind is no longer sputtering materials on the moon. Once you go into the magnetotail, the solar wind is gone. It's shielded. So what's taking place is that you're actually seeing a decrease in the amount of sodium. But as Menelaus Sarantos will tell you a little later in the meeting, the vaporization due to impacts is still continuing, and so that may explain some of what we see here. Once the moon exits the magnetotail, you see a sudden increase in sodium on either side, on the following side, just because the sodium has sort of been, the reservoir has been replenished on the surface, and now sputtering is taken over and is actually producing an excess of sodium coming out into the exosphere. Not only sodium, but potassium. Here's sodium in blue as a function of date. This is column abundance. And Tony Colaprete will talk about this and more later on in the meeting. Sodium and potassium do go together in some respects. There is some correlation here, but this may the lack of correlation in some respects. These are full moons, hence magnetotail crossings. That's what's in yellow. The gray guys are identified showers. Sodium definitely responds to shower activity. It's not clear that the potassium does. It did in this case. But there's a lot of physics going on there, and I'm not prepared to talk about it at this point, but that's what's coming out of the UVS data, and you'll hear more about that later in the meeting. So as far as UVS is concerned, these are other, this is the rest of this chart, the things we're meant to look for. What we've seen, obviously, we've seen potassium and sodium. It looks as though we've seen oxygen. It looks as though we may have seen OH with UVS. It looks like there's a possibility of seeing H2O plus with UVS. There's an upper limit on silicon. Let's see, an upper limit on aluminum, magnesium, calcium, and so on down the list, titanium and iron. These are estimates based on preliminary data, and you'll see more on that as time goes by. So just very quickly, I wanted to show, oh, that didn't come across very well at all. I apologize to Mihai Harani for that messed up graphic. It's meant to show dust density as a function of altitude. I can just show it this way. LDEX measured dust grain sizes and abundance density as a function of altitude. This is density running along the horizontal axis here, and altitude shown vertically. So what's interesting about this is, as you might expect, is the density goes up as you approach the lunar surface, but then it kind of plateaus out at a certain level within a few tens of kilometers of the surface. And one thing we'll be seeing more of is some of the very lowest altitude data that kind of puts the rest of that into perspective. This is another way of presenting it. I don't have time to go into that, unfortunately. I apologize. But basically, we've met all the requirements for measuring dust. The dust is very, very tenuous indeed. This is 2 times 10 to the minus 10th per cubic centimeter for these 1 micron dust grains, far, far less than what we were intended to look for. And then there's a small size fraction that was really, the question was whether this was levitated dust. And we haven't seen any evidence for levitated dust. We looked for it with our star trackers, didn't see it. And so with the steely eyes of Yvonne upon me, I'll let you read the summary here.
Okay, so we're going to take one question, but before we do that, I want to ask Jasper to go ahead and get mic'd so that you can be ready to go. All right, do we have any questions here for Rick? Don't tell me I've intimidated everybody that much.
Intimidated me.
Okay, all right, well, are we ready to go though? Oh, shoot. Come on down here.
Use this
We'll
one,
just do
Jasper.
this one.
Come here.
Okay, yeah, in the future, I think we do have 2 sets of these, right? So if 5 minutes before the end of the talk, the next speaker can go